is the basic principle and construction, right? So two half cells make a full cell. Half cells are made by electrode, electrolyte, and both of the electrodes of the two half cells are connected through wire, through a voltmeter that will gives us the voltage, and there is one, a salt bridge that maintains the charge balance of the electrolytic solutions. That's why a cell continues to produce electricity. Did you get me? So this is, about the construction. What happens next? How will you know what voltage we will get? How will you know how much electrons are produced in the oxidation half cell and how much electrons are received in the reduction half cell? That's why we must know now that what is electrode potential. By knowing the electrode potential, what happens? By knowing the electrode potential, we can predict how much electrons are produced and how much electrons are received. Okay, we'll discuss about electrode potential. So that's why we must have an idea how readily, to which extent an electrode is ready to receive or lose electrons. That's why we created one term is electrode potential. The tendency of an electrode potential. Okay. So the tendency of an electrode to gain or lose electrons is called the electrode potential. But how to measure it? What is the problem? Why we can't exactly know how much of electrons is produced or how much electron is received by an electrode? What's the problem? Let me make you understand. Okay. First of all, you can't measure the electrode potential of a single electrode. Single electron, I mean, when it is not connected to another half cell, right? So if I will take only one vessel containing here zinc sulfate, okay, containing here zinc sulfate, and one zinc electrode is dipped. Only when zinc electrode is dipped into zinc sulfate, there will be no production of electricity. There is no production of electrons. Electrons are only produced when it is connected to another half cell. Say again, once again I am showing you that is copper sulfate in which a copper electrode is dipped and both of them are joined through a voltmeter. Once again I am showing you the cell. Okay. So you see, in zinc sulfate and copper sulfate, what happens? When this zinc electrode is connected to the copper electrode, say this is copper electrode, this is zinc electrode. So the extent of electron production from the zinc side, from the zinc electrode, when copper is connected to it, is not the same when that zinc electrode is connected to another half cell. How you see? Say a silver nitrate electrolyte in which this is the electrolyte and a silver electrode is dipped into it. Same zinc electrode when joined to silver electrode, the extent of electrons are not the same which are flown through the air. Right? Why? So, if you are not able to receive what I am giving you, so I can give you more. So both of them should be ready. Both of them should be ready. So the extent of electrons that flow through the wire depends upon the depends upon the producing capacity and the receiving capacity of electrons, receiving capacity of the electrodes. Okay. So the quantity of charge means the number of electrons that will flow through the wire depends upon both of the half cell. It is a relative thing, so we cannot measure the electrode potential of a single electrode, nor when we also cannot measure the exact electrode potential of an electrode when it is joined to any electrode. That's the main problem. So we should need a reference. Now the reference electrode. This is a reference electrode. Here what should be done? That reference electrode is nothing but SHE. Okay, reference electrode is the standard hydrogen electrode. What is the standard hydrogen electrode? We must see what is the construction. Okay. So it is a half cell taken for reference. Okay. What are the constructions? Very simple. There should be a vessel. It should contain first of all, electrolyte. The electrolyte is 1m HCl. 1m HCl. Inside which one glass tubing is here, and your one platinum wire connects to a platinum plate. This platinum wire connects to a platinum plate, and through which hydrogen gas at 1 atmospheric pressure is bubbled through it. So the construction is a platinum wire connects to a platinum plate. The electrolyte is 1m HCl, and hydrogen gas at 1 atmospheric pressure is bubbled through it. Now, so this is the standard hydrogen electrode. As I said, this is the platinum wire, and this is the platinum plate, over which finely divided platinums are pasted, over which hydrogen gas can be absorbed. As you know, platinum has great affinity for hydrogen. Okay. So once you made ready the reference electrode, now you can join any of the half cell with it to have a standard value of electrode potential. Since it is a reference, now we can compare the electron producing or electron receiving capacity of an electrode. How? So let us first consider the electrode potential of zinc. Okay, so now we have to connect this zinc half cell to the standard hydrogen electrode to measure the electrode potential of zinc. So what should we do? Here, as we said, this is the zinc sulfate solution, and we should take 1 molar concentration. You see why we are taking 1 molar concentration. So as we said, the electrode potential, there is another term, standard hydrogen electrode. Okay, standard electrode potential. Standard electrode potential. Electrode potential to standard electrode potential. Okay, what is the standard electrode potential? When we measure the electrode potential at standard state, what are the standard states? When we measure the electrode potential, taking the concentration of the electrolyte should be 1 molar. Temperature should be 25 degrees centigrade, the room temperature, and the pressure, if any, should be maintained 1 atm. If you measure the electrode potential at these conditions, then the electrode potential will be called as standard electrode potential, and that's why in standard hydrogen electrode we have taken 1 molar hydrogen chloride as electrolyte. Well, we have also taken the 1 molar concentration of the zinc sulfate solution. Okay. So in the zinc sulfate solution, we will have to dip a zinc electrode. Okay, we will have to dip a zinc electrode, and this zinc electrode must be connected to the hydrogen electrode. And as usual, there should be one, what is this? Yes, salt breeze. Okay. Now you see what happens when you connected this zinc half cell with the standard hydrogen electrode. After some time, when we got a steady voltage, when we get a steady voltage of 0.76 volt. In particular these conditions, we can make an experiment and also we can get that steady constant voltage of 0.76 volt. Then how to measure the electrode potential? It is now very easy to understand. Okay, you see, let me tell you that this voltage is due to the extent of electrons that is flowing through the wire, and again the extent to which electrons are flowing through the wire depends on how the electrons are produced in the oxidation half cell and how much electrons is produced in the reduction half cell. But problem once again is which of them is the oxidation half cell and which of them is the reduction half cell. Did you get me now? So after some time, when you got a steady voltage, when you measure the concentration of hydrogen ion inside this standard hydrogen electrode, the H plus ion concentration was observed to be less than 1 molar. But we have taken 1 molar hydrochloric acid. So that means it should give us the concentration of hydrogen ion 1 molar, but we are getting less than 1 molar. That means hydrogen ion has been used up to give hydrogen gas. Each hydrogen ion must receive 1 electron to give H. Such like this, 2 hydrogen ion receiving 2 electrons give hydrogen gas and is released. So since the hydrogen ion concentration is decreasing in this chamber, that means here electrons is received by the hydrogen ion and becoming H2. So since electrons received, this is the reduction half cell. The standard hydrogen electrode is now in this case only reduction half cell. Okay, reduction half cell. So definitely, if electrons is received, S plus ions here there are S plus ions. Those S plus ions are receiving the electrons coming from here, and since reduction is taking place here, then oxidation must taking place in this chamber, zinc half cell. How? So zinc is being oxidized to give Zn2 plus and 2b minus. The electrons produced in the zinc half cell is flowing through the wire and received by the H plus ions, and H plus ion being H2 is released. So we knew now which of them is the oxidation half cell, which of them is the reduction half cell. Okay. Now it is very clear that the voltage we are obtaining, that steady voltage of 0.76 volt, is due to the extent to which the oxidation half cell is oxidized and the reduction half cell is reduced. So we can say this voltage is a result of the oxidation potential of this electrode and the reduction potential of this electrode. Oxidation potential means the readiness, the tendency of an electrode to be oxidized. Reduction potential means the extent to which one electrode wants to be reduced. So whatever effect of the oxidation potential and reduction potential is nothing but this voltage. So now we have made a cell. It is nothing but a cell, no? So now the voltage will be called as cell potential. This cell potential is a combined effect of oxidation potential and reduction potential. Okay, so we will write accordingly a formula. Okay, so we can write the electrode potential we got, the cell potential we got, the cell potential, and we call it EMF, electromotive force, cell potential. If we measure them at standard state, then that will be called as standard cell potential. We write it E.Cell. Is nothing but the combined effect of both of the halves I have already mentioned. So is equal to oxidation electrode potential of anode. You see, let me tell you that from now, whenever I will write anode, you will have to take it oxidation electrode. The electrode where oxidation takes place is the anode. You see, you remember it. Anode means oxidation half cell. Cathode is inside reduction half cell. Remember it. Okay. Remember it. Okay. Write it down. So now the standard cell potential is equal to oxidation electrode potential of the anode plus reduction electrode potential of the cathode. Okay. So the first formula is nothing but the E.Cell means standard cell potential is equal to the sum total of the oxidation electrode potential of the anode and reduction electrode potential of the cathode. And accordingly we can develop this equation continuously. In this instance, in this example, zinc was being oxidized, hence zinc acts as anode where oxidation takes place. And SHE in standard hydrogen electrode, you know what happens? The reduction takes place and that acts as the cathode. Did you get it? So accordingly, we will give a notation to both of these. Okay. So you now see, you are saying oxidation electrode potential of anode. If we will change this reduction into oxidation, then I can change this sign positive to negative. So I can write E.Cell is equal to oxidation electrode potential of anode. When I change this positive to negative, this reduction once again is changed to oxidation. Oxidation electrode, all other terms will be remaining there. Oxidation electrode potential of cathode. This is one another formula. Similarly, if you want to, that means make it as usual to be retained in the equation, and if you want to change this oxidation into reduction, that should get a negative sign. So accordingly, you can also get E.Cell is equal to take it to the first reduction electrode potential of cathode minus reduction electrode potential of anode. Okay, so this formula particularly is of greater importance because nowadays the electrode potential of all the electrodes are generally expressed in terms of their standard reduction electrode potential. That's why this formula should be that means remembered with importance. Okay. So how to give a notation? See now, since we have taken the standard cell potential E.Cell to be the oxidation electrode potential of the anode. Here the anode is nothing but the zinc half cell where oxidation takes place, and the redox with it we should add the reduction electrode potential of the cathode. In this instant, this is standard hydrogen electrode. Are you getting me now? So we can now write standard cell potential E.Cell, which we have already measured from the voltmeter to be 0.76 volt, is equal to the oxidation electrode potential of zinc half cell or anode in this case. How to represent it? It is represented like this. E0 in the oxidation half cell, it is becoming E0 Zn becomes Zn2 plus. This is the oxidation half cell. Charge is increasing, and by this notation, since 0 to 2 plus, it is mentioning you the oxidation electrode potential plus this is E0 plus. In the standard hydrogen electrode, what happens? Hydrogen ions being reduced. So 2H plus receiving electron to give H2. This is the perfect notation now. This is, we can say, the oxidation electrode potential. Charge is increasing of the anode and the charge is decreasing plus to 0. That means reduction. The reduction electrode potential of the cathode. So conventionally, let me tell you one thing, that when we constructed the standard hydrogen electrode, we have conventionally taken the electrode potential of that standard hydrogen electrode to be 0, so that whatever you have to connect all those electrodes with that, so there is no problem. So we can write, so its electrode potential, in the note you should write standard electrode potential of SHE is conventionally taken as 0. So implies 0.76 volt is equal to E0 Zn2 plus 0. That means this is equal to this. So E0 Zn2 plus means this is the standard oxidation electrode potential of zinc is equal to 0.76 volt. Thus, we measure the electrode potential of the zinc electrode. Did you get me now? So we can write, you see here, E0 Zn2 plus Zn2 plus Zn means this is standard reduction. Since charge is decreasing 2 plus to 0, reduction electrode potential of zinc, just the negative sign of it. Since this is being converted oxidation to reduction, this should be 0.76 volt. 0.76 volt. I now think that you got properly what is electrode potential, what is standard electrode potential at the standard state when we measure, what is standard hydrogen electrode, that is our reference electrode, with which you have to couple another half cell for which you want to calculate the electrode potential. Are you getting it? So how to determine the standard electrode potential of copper electrode? Here also we will have to couple the copper electrode, the copper half cell with the which one? Reference electrode. What's that? Standard hydrogen electrode. Did you get me? So after you couple them, now a steady voltage, steady means constant voltage of 0.34 volt is observed. Once you get a constant voltage you see what happens, well, right? You see 0.34 volt is equal to, it's a combined effect of the oxidation electrode potential and the reduction electrode potential. But once again, how to know which of them is the oxidation electrode and which one is the reduction half cell? Okay, so how to confirm? So after you get a steady voltage, when you titrated the hydrochloric acid solution inside this chamber in the standard hydrogen electrode, what happened? It was observed that the concentration H plus ions was greater than the previous 1 molar concentration. Okay, since H plus ion concentration is greater than 1 molar, are you getting it? So now we are that previously we have taken only 1 molar concentration of hydrochloric acid, but it is now greater than that of taken already. So it is clear that hydrogen ion is being produced. How is being produced? Because the hydrogen, in SHE you are supplying what? Hydrogen gas at 1 atm. So that hydrogen gas is now decomposing to give 2H plus ions. That hydrogen gas is giving you 2H plus 2E minus. In this manner, hydrogen is produced, hydrogen ions are produced, and electrons are produced. If electrons are produced here, they flow through the wire and are received here. So how the electrons are received? The Cu2 plus ions present in this electrolytic solution, that Cu2 plus receive the electrons 2E minus, 2E give the copper and are deposited here. Did you get me? So the electrons are produced in SHE, flow through the wire and received in the copper chamber. So electrons are produced here, means this is the oxidation half cell, then this is the reduction half cell. Reduction takes place here and oxidation takes place here. So this steady voltage 0.34 volt should be equal to the oxidation electrode potential of SHE, which is conventionally taken as 0, plus the reduction electrode potential of copper. Did you get me? We'll write down. So 0.34 volt is equal to oxidation electrode potential of anode. Here the anode is SHE, where the oxidation takes place, plus the reduction electrode potential of cathode. Here the cathode, where the reduction takes place, is the copper half cell. Okay. So or the copper electrode. Okay. So we'll write implies 0.34 volt is equal to, conventionally taken as 0, plus the reduction electrode potential, reduction. Okay, since this is the standard electrode potential, standard cell potential, we can write 0.34 volt standard. Since this is the standard cell potential is equal to 0.34 volt, so we can write this standard cell potential implies this is the what? E0 cell is equal to 0.34 volt. Conventionally this value is taken as 0 plus standard reduction electrode potential of copper. This should be written as Cu2 plus 2Cu. Okay, so implies E0 Cu2 plus Cu is equal to 0.34 volt. So we have taken two examples how to determine the electrode potential, standard electrode potential of various of zinc and copper. Similarly, we can couple different electrodes with the SHE to get their own values of standard electrode potential. Once you know the standard electrode potential of various electrodes by coupling them with this reference electrode standard hydrogen electrode, then you can do what? Then you can measure the cell potential by coupling different electrodes. You may or may not couple them with the standard hydrogen electrode. How? So let us now couple that zinc copper cell and measure the cell potential. Okay. Cell potential can be calculated by the formula we have already derived. The cell potential, standard cell potential should be equal to E0 cell is equal to reduction electrode potential of cathode minus reduction electrode potential of anode. Reduction electrode potential of anode. So how to know who of them will be the cathode and who of them will be anode. Okay, so it's the next challenge. It's the next challenge how to determine who of them will be cathode and who of them will be anode. We can study it from the electrochemical series. Okay, in the next video I will show you what is electrodepotential series or electrochemical series, from which what are the applications, and after that how one of the application will be there to identify who of the electrode, who of the half cell is the oxidation half cell and who of them will be reduction half cell. Okay, thank you.